This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, professor for this class, and this is lecture 24, the first part of a couple of lectures on chemical vapor deposition. Our reading is chapter 13 of our textbook by Campbell. Chemical vapor deposition is different than the previous deposition topics we've covered, physical vapor deposition, in that chemistry is involved in the creation of the material that makes up the film we're depositing. CVD is used to deposit most of the dielectrics that we use in semiconductor manufacturing, also silicon, in either an epitaxial or polysilicon form. We'll talk about those later. But also for some metals, we can do CVD tungsten and tinitride, for example. It's performed in furnaces, often furnaces that look a lot like the oxidation and diffusion furnaces we've seen before. They could be a stack of furnaces, and from the outside you might not even know the difference between an oxidation furnace or diffusion furnace and a CVD furnace. But there are other configurations as well, including newer single wafer reactors. The trend in the semiconductor industry over the last couple of decades has been moving from batch processing to single wafer processing. It enables more flexibility and control in the manufacturing process. But nonetheless, there's still a lot of batch processing done for these long process steps like oxidation, diffusion, and sometimes CVD. What makes CVD different than other types of deposition processes is that the film reacts, is created by chemical reactions that occur on the wafer surface and create the film that we're depositing or growing via that chemistry. That's very different than physical vapor deposition, where there's no chemistry occurring in the creation of the film. So, what kind of things can we do with chemical vapor deposition? One way of separating the styles is to think about where the reaction occurs. One possibility is that the reactions occur in the gas phase. So a homogeneous reaction means that both reactants are in the gas phase at the time they find each other and react. We produce a solid that then floats around and lands on the wafer. This turns out to be not very good. Some very early CVD systems were homogeneous gas phase reactions. The result is poor uniformity, lots of particles, defects that are caused by these particles can be a real problem. So we tend to avoid at all costs, usually, any gas phase reactions that produce a solid. Instead, we want the reactions to occur on the wafer. The solid surface reaction is also called heterogeneous reactions. The reactions occur on the wafer surface, various components adsorb to the surface, a reaction, and a solid is formed. That solid that's formed is the deposited film, and it's right where it needs to be when the reaction takes place. This is what we're trying to achieve, and we adjust the reactions, the chemistries, the concentrations, the configuration of the chambers to encourage heterogeneous reactions rather than homogeneous reactions. Let's look at a very simple mechanism for CVD reaction. The simplest one, in fact, that we can even think of. It'll tell us a lot about more complicated mechanisms, but it ignores necessarily many things that could be happening. In fact, full modeling of real CVD reactions can be immensely complicated. There can literally be dozens or hundreds of different chemical reactions occurring simultaneously in a CVD furnace. That's because we have a lot of reactants, we have very high temperatures, a lot of different things can happen. But we're going to simply look at a two-step mechanism to give us a basic idea of what's happening. First, we have the reactants in the gas phase, and they need to be able to move to the wafer surface where the reaction is going to take place. So there's a diffusion step, a gas mass transport operation. Then the reactions are adsorbed onto the surface of the wafer, and finally at the surface there's some reaction that takes place. we're going to assume that this is the rate limiting step so that we can ignore the last two steps, which is the desorption of the byproducts and the transport of those byproducts into the gas stream. We want to make sure that those two steps are not rate limiting because that makes for a much slower reaction. So, with the assumption of the reaction at the surface is the rate limiting step, we only have to worry about two fluxes. The first flux is the diffusion of the reactant from the gas phase to the surface. This diffusion will be given, a diffusion flux will be given by Fick's first law of diffusion. Here, d is the diffusivity of the reactant in the gas. dC dx is the concentration gradient, and we'll approximate the concentration gradient as a difference, the bulk minus the surface concentration, divided by some distance over which that difference occurs, which we'll call the boundary layer thickness. So over some boundary layer thickness, we go from the bulk to the surface concentration, and we'll approximate the derivative with a difference. Then we'll lump the diffusivity of the reactant in the gas divided by the boundary layer thickness and call that the mass transfer coefficient H sub G. Pardon me. If this looks familiar to you, it should. This is the exact same first step we used in the derivation of our oxidation mechanism. The Deal-Grove model of oxidation started with the diffusion of the oxidant from the bulk to the surface of the wafer. So this step is the same, but now we've got a second step that occurs at the surface. It's simply a reaction. The reactant has a certain concentration at the surface, and then we get a reaction and a flux of reactants that is proportional to that surface concentration. So we're assuming a very simple first order mechanism. Maybe it's a dissociation of a molecule, for example. And we have a rate constant K sub S. These two steps will form a steady state so that reactant is supplied to the surface at just the right rate to supply the reaction. We'll get the two fluxes being equal to each other, and we'll call that the steady state fluxes. And then at steady state, we can solve for the unknown concentration, which is C sub S, the concentration of the reactant on the surface. We solve for that and get the value shown here. And the result is a simplified rate equation. The steady state reaction rate is some overall or total rate constant K sub T. The T, capital T here, represents a total or overall rate constant, multiplied by the concentration of the reactant in the gas phase, in the bulk. This total rate constant you see is a function of both the surface reaction rate constant, K sub S, and the mass transport coefficient, H sub G. Now, we want to turn this reaction rate, which is a flux, number of atoms per unit area per unit time, we want to turn that into a growth rate. What is the deposition rate, the rate at which the thickness of the film increases with time? To do that, we simply need to know the number of atoms per cubic centimeter in the deposited film. That's the atomic density of the film that's being deposited, and the deposition rate, V, is simply the steady state flux divided by this density, N. The deposition rate is measured in thickness per unit time, nanometers per second, or angstroms per minute, or whatever we feel is the best. Then we can combine these things to get an overall deposition rate. So we have our overall rate constant, K sub T, it's divided by N. We convert our concentration, C sub G, into a partial pressure in the gas, P sub G, and we'll just assume the ideal PV equals nRT, ideal gas law applies, and we're left with P sub G, the partial pressure of the reactant in the gas phase, divided by KT, where K here is the Boltzmann's constant. We'd use R if we had different units. So either way, it depends on the units that we're using. So what do we have? We've got a rate of deposition that is proportional to this rate constant case of T times the partial pressure of the reactant in the gas. And as I said, this is the simplest possible rate equation that we could derive. It's overly simplified. The idea is not that we're actually going to be predicting specific deposition rates for specific chemistries, but we want to get a feel for the overall trade-offs that are involved, the overall effects, and how they control the deposition rate. So let's take this simplified rate equation, the deposition rate given here as a function of the rate constant case of T, which is shown here. We're going to find that there's going to be two regimes that this deposition can occur in. In one regime, the rate constant of reaction at the surface is much, much bigger than the mass transfer coefficient H sub g. When that happens, take a look. If Ks is much bigger than Hg, I can ignore Hg in the denominator here. Therefore, the Ks's cancel, and I get the overall rate constant Kt is about equal to Hg. In other words, we're diffusion controlled. If the reaction at the surface is very fast, we're limited by the rate at which we can diffuse new materials from the bulk to the surface. So we say it's a diffusion controlled regime or a diffusion limited regime, and the overall deposition rate is controlled by Hg, how fast material can diffuse to the surface of the wafer. Another regime is when Ks is much, much smaller than Hg. If the surface reaction rate constant is very small, we can supply through mass transport as much reactant as we need, and we're limited by how fast it reacts at the surface. In this case, Hg is much bigger than Ks. I can neglect the Ks in the denominator. The two Hg's cancel from top to bottom, and we're left with Kt is about equal to Ks. This is the reaction-controlled regime. And we're going to find that these two regimes are very different in their behavior, and they determine a lot of different things about how we do CVD. If we're in the diffusion-controlled regime, we do CVD in one way. If we're in the reaction-controlled regime, we do CVD in a very different way. So knowing which regime we're in is the fundamental thing we have to understand to figure out the right way to do chemical vapor deposition. Now, one other thing to note. Pg, this is the partial pressure of the reactants in the gas. And the deposition rate is proportional to that quantity. You can imagine that we want high deposition rates. Throughput is very important in any manufacturing operation. If I have a very low throughput, I have to buy more furnaces. If I have a very high throughput, I can afford to use fewer furnaces, and I get better cycle times in terms of getting the product out through the factory and out the door. So we like fast deposition times, rates rather. So we'd like Pg to be large, but there's a problem. The problem is we want our reactions to be in the heterogeneous regime. That is, we want the reactions to occur on the surface of the wafer, not out here in the gas, in the bulk. And if the partial pressure of the reactants gets too large, they'll find each other in the gas. If they find each other in the gas phase, they're going to react in the gas phase and cause particles that then fall off and drop on our wafer and cause defects. This is a big problem. We try to prevent homogeneous reactions. How do we do that? We keep the partial pressure of the reactants low. Now, we still get heterogeneous reactions to occur because one reactant may land on the wafer and then another reactant will come and land as well. Since the first one is already sitting on top of the wafer, it's just waiting there, I can get a faster reaction rate than if both of them are wandering around randomly in the gas. They don't find each other as frequently. And that's how we can control the amount of homogeneous reactions versus heterogeneous reactions. So we'll see this throughout. The partial pressure of the reactants tends to be quite low in these reactors. Let's finish up this first part of our series on CVD, our two-part series on CVD, by looking at the effects of temperature on the deposition rate. Now, we have two pieces, two steps. We've got a reaction step and a diffusion step. So diffusion of the bulk material to the surface and then reaction on the surface. These two steps have different activation energies. In general, the activation energy for the surface reaction is much, much, much greater than the activation energy for gas diffusion. In fact, we tend to think of the diffusivity of the material in the gas as having a non-exponential variation with temperature. Here I show temperature to the 3/2 power. Actually, there is probably an Arrhenius-like E to the activation energy over KT term as well, but the activation energy is so small that sometimes we could ignore it, and we get this T to the 3/2 power. The boundary layer thickness delta also varies with temperature, but quite slowly. The result, the mass transport coefficient, recall, is the diffusivity divided by the boundary layer thickness. That thing varies slowly with temperature. Goes as T to the 3/2 power or something like that. Whereas the reaction at the surface varies exponentially with temperature, with a fairly large activation energy. The result is, at high temperatures, the surface reaction rate constant gets very large. The bigger the temperature, the larger the reaction rate constant. But Hg doesn't change very much with temperature. It changes very slowly with temperature compared to Ks. So Ks gets bigger and bigger and bigger, and at high enough temperatures, we enter the diffusion limited regime. At low temperatures, Ks gets smaller and smaller and smaller until we can enter the reaction limited regime, where Ks is much smaller than Hg. Now, we switch regimes from diffusion limited to reaction limited by changing the temperature. And the reason is the reaction has a very high activation energy, and its rate constant changes a lot with temperature. Mass transport has a low activation energy. Its magnitude of the mass transport coefficient changes very slowly with temperature. We can see this behavior by plotting the deposition rate versus 1 over temperature. This is called a pseudo-Arrhenius plot. An Arrhenius plot plots the rate constant versus 1 over absolute temperature. And the rate constant is put on a logarithmic scale. That's called the Arrhenius plot. We're doing something similar to the Arrhenius plot. Instead of plotting the rate constant per se, we're plotting the deposition rate, which is proportional to the rate constant. So we call it a pseudo-Arrhenius plot because it has some of the same behaviors. And what do we see? Out here, we're at the low temperature regime. So 1 over T is big, that means temperature is low. And we have a steep variation in deposition rate with temperature. The slope of this curve is something like the activation energy divided by KT. Activation energy divided by K, the Boltzmann constant. So the slope of this curve is essentially proportional to the activation energy. In the reaction limited regime, we have a steep slope, a high activation energy. Then we make a transition to the diffusion limited regime. So down here, reaction limited. Up here, diffusion limited or diffusion controlled. You see that the rate is not changing much with temperature when we're in the diffusion controlled regime. And we can pull off an activation energy here, but it's probably not even exactly a straight line kind of behavior because we have that extra T to the 3/2 power factor in there. In any case, the difference in the slope is quite dramatic. We have a transition region between the two. But as we'll see next time, how we design a CVD system to work in the reaction control regime is very different than how we design a system to work in the diffusion control regime. Why don't you think about that a little bit before you watch the next lecture? What would change about the design of a reaction chamber if you were in the reaction control regime versus if you were in the diffusion control regime. The other thing I'd like to point out, what did I say about deposition rates? We want high deposition rates, right? Where do you get the highest deposition rates? The diffusion controlled regime. If we are solidly in the reaction control regime, we tend to have a lower deposition rate. And this will also play into our choices about what kind of a CVD system we would like to have. So let's look at what we've learned. You should be able to answer all of these questions very quickly and easily. If you can't, you need to go back and review some of this material. First, why is heterogeneous CVD preferred over homogeneous CVD? What are the two steps in our very simplified two-step mechanism for chemical vapor deposition? Explain the difference between a diffusion-controlled regime or a reaction-controlled regime for CVD. And that's the end of our presentation. We'll finish up with part 2 next time.